So our last chapter is about inference on linear regression models. So this particular video is going to mostly talk about what conditions need to, and how to check for the conditions if we want to either perform a significance test about the slope of a regression line, whether that's a confidence interval or a significance test. The other things we're going to do more in class, but I will touch on them a little bit in this video. So when we look at a scatter plot and it shows a linear relationship between a quantitative explanatory variable and its quantitative response variable, we can use a least squares line to the data, fitted to the data, to predict y when we have a given value of x. And if the data has been collected from a random sample from a larger population, then we can use statistical inference, much like we've been doing with other situations, to answer questions that would normally be answered with a line of fit. So if there's is there really a linear relationship between x and y, or could it just be chance? And so we're talking there about a significance test. And in the population, how much will the predicted value of y change for each increase of 1 unit in x? That margin of error is going to be our margin of error of slope, and that's a confidence interval. So we're looking at some of the things we've been working with in the past, but specifically with linear regression. So this next couple of slides is going to take us from a population and the information about the population, and then make connections between the sample and how we can use that information from the sample to make inferences about that population. So remember, we're studying the population so we understand the sample. So then moving forward, we'll only have a sample, and we can see how we can use that sample to make inferences about the population. This particular population is the 222 recorded eruptions in a single month of the Old Faithful geyser in Yellowstone. And the things that you're looking at are the duration of the eruptions, and as it relates to the interval of time between that eruption and its next eruption. So the regression here is the true regression line, because it's all of the observations. We're calling that the population in this case. So that least squares regression line is y-intercept is at 33.97, and this says that it's going to be 10.36 minutes more in between eruptions for every minute that the geyser has actually erupted. We're now going to go ahead and take a sample of this and see how the sample regression line relates to the population. So here, an SRS of 20 was taken from each of the 222, and we notice that the sample y-intercept is quite different and the sample slope is quite different. Varies quite a bit from the population regression line. However, when we look at a lot of them, we see all of the possible b-values. It's roughly symmetrical and unimodal, and the center, the mean of all the b-values is that 10.35. It's very, very close to the true regression line. And then the spread, the standard deviation of 1,000 b-values is 1.29. Later we will see that the standard deviation of the sampling distribution of B is actually 1.27. So we're talking about looking at the unbiased estimators in the sampling distribution here. So if we choose an SRS of n observations of a point xy from the population of size n, with a least squares regression line following the predicted model. So predicted y is going to be this y-intercept plus the population, the true population slope, times x. Then the b, which is your sample slope, the mean of the sampling distribution of b is approximates the true slope, and the standard deviation of the sampling distribution of b, please excuse me, is the true standard deviation, sharks are winning, divided by the standard deviation of x times the square root of n, as long as the 10% condition is satisfied. And then the sampling distribution of B, when you're talking about the shape, is approximately normal if the values of the response variable y follow a normal distribution. So we're talking here about what does the sampling distribution of B tell you. Just a little reminder about why we check conditions. For one, we check random because if the information wasn't collected randomly, it is useless to inferring for any population. Bias, known or unknown, might be present, and so if it's not randomly collected, throw it out, get a better sample. Each trial or subject needs to be independent, and so if we're sampling without replacement, then we need to make sure that we aren't sampling more than 10% of the population. So if that is not met, then we can't use our standard deviation formulas. And then the reason we check normal, if it's normal enough, then we can use Z and T scores. And the way we check it with proportions is n times p has to be greater than 10, successes, and failures, n times 1 minus p have to be greater than 10, and all the rest of them are going to be dealing with large counts to check, or we have to check for skewedness. With categorical chi-squares, we're going to make sure that all our expected counts are greater than 5, and linear regression, this is how we're going to check. Just like regular, our data has to come from a well-designed random sample. We have to check the 10% condition only if we're sampling without replacement. If we're dealing with an experiment, we don't have to check the 10%. And normal, there's a couple that we're going to be looking at, either a histogram or a normal probability plot to check to make sure that the y value is according to a normal distribution. And then there's two more pieces that we have to pay attention to. For one, we have to make sure that a linear model is actually appropriate. And we're going to do that by looking at a residual plot. And we're going to do use the same tool, the residual plot, to help us figure out if the standard deviation of y is about the same for all the values of x. It's called the equal standard deviation or equal variance condition. So we've checked to make sure our data was collected using an SRS, a simple random sample, and we've checked the 10% condition if we're sampling without replacement. Now we have some options when we want to check the normal condition. There's no magic number with linear regression, so you actually have to do some graphing, and you have your calculator do it for you. If you see skewness, you cannot run any of the inference tests. If you see the skewness either in a histogram or in a normal probability plot, then you're going to go ahead and say, no, I can't do this. This particular histogram and this particular normal probability plot, you notice how it's a straight line without any curving or skewing. These two, go ahead and run it. These two, nah. So checking for normal, either histogram or normal probability plot, look for skewness. Some things you have to check that you don't have to check for any other inference test is the linear model appropriate? And so that's when you're looking at your residual plot. Here's your residual plot of something that is absolutely not a linear model because you're having that residual of a pattern that is not random. So if this was it, you could not run an inference test on this because a linear model is not appropriate, whereas this scattering shows that a linear model is perfectly fine. And the second thing you need to look at is when you've got your residual plot, is the data fairly equally above and below the line as the values of x get bigger. And this one shows as the values gets bigger, y gets bigger, or as the values of x get bigger, y gets smaller. Neither of these would be appropriate because they do not have an equal variance. So we want a fairly equal variance for us to be able to run an inference test. What we're working on now, if our conditions are met, we want to be able to take a sample, a well-taken sample, and make some inferences about the true population or the true regression line. And this true regression line would allow us to make some predictions about y based on the slope and the y-intercept of the population. But we're going to make some predictions just using a sample, and so we have to figure out what our unbiased parameters are. We find out that the slope b, which is the sample slope, is an unbiased estimator of the population slope, capital B, and then beta. And then the y-intercept is an unbiased estimator of the population y-intercept A. So then the only remaining parameter we need when we do these inference tests is standard deviation. And like always, we do not have very often the population standard deviation, so we're going to have to use some sample work. And so the least squares regression line computes from the sample data. It estimates the population regression line. So the residuals estimate how much y varies about that population line. So we're going to go ahead and use, since we don't have that population standard deviation, we're going to estimate it by looking at S, the standard deviation of the residuals. And here's the equation for it. A residual, by the way, is always observed minus predicted. And then they do all this other stuff to find the standard deviation. So we're going to go ahead and use as our parameter for variance the S, which is the standard deviation. As usual, we don't normally know the population standard deviation, so we estimate it with the standard deviation of the residuals S, which you're always going to see on those min-tab displays. Then we can estimate the spread of the sampling distribution then with the standard error of the slope, and so that's going to come from the residual. Whoops, my bad. From the standard deviation of the residuals, the standard deviation of the x value, or the explanatory variable, times the square root of n minus 1. And the sampling error just tells you, after lots and lots of simulations or lots and lots of looking at the samples, the error in the slope is going to be this number, whatever the standard error is. And then we can transform the values of b by standardizing, but once again, we don't have that standard deviation of b, so we're going to go ahead and like any time we don't have the population standard deviation, we have to use the sample standard deviations. We end up with a t distribution as opposed to a normal distribution, and we have to pay attention to the degrees of freedom. And for reasons beyond the scope of this class and beyond me, the t-distribution for a linear regression inference test has an n minus 2 degrees of freedom. So in our particular case, we had a slope of around 10, and then when we standardize it, that of course becomes 0, and then our standard error is from there to there, and then we're going to go ahead and standardize that. So if we're running a confidence interval and trying to decide the margin of error and such for the possible slope of the true population regression, it's the same form we've always been using: the statistic plus or minus a critical value times the standard deviation. And so in our particular case here, our statistic is the sample slope. We're going to have to use a t-star based on the level of the percent confidence we want, and then our standard deviation in this case is going to be the standard error of b. And once again, we've got to remember that the degrees of freedom is n minus 2. So if we have our conditions met, the slope b can be used to construct a confidence interval that gives us the range of values, plausible values for the true population slope, the population's true regression slope. But we can also perform a significance test to determine whether a specified value of b, the population slope, is plausible. And then the null hypothesis in this case is always going to be that the null is that b is that hypothesized value, and then we test to see if that's plausible. So our test statistic always comes from statistic minus parameter divided by the standard deviation. In this case, it's going to be b minus whatever our null value is. So the slope that we got from the sample minus whatever our null value decision is, and then divided by the standard error of b. And once again, the t-distributions here are always going to have an n minus 2 degrees of freedom. So this has mostly been about the conditions and a little bit about the significance tests and the confidence intervals, but we'll do a lot of that in class, and if necessary I will come back and do a video on these other things as well.